and exercise science in R. Today we're going to be covering caloric expenditure, and we're going to be calculating this using VO2 or V.O2 max estimates, and then converting that into calories that we've expended over the course of a 10-kilometer race. So we're going to start here. My name is Aaron Pearson. You can find me at midsprint.io, and you can also find me on Twitter at Aaron Z. Pearson. For those that are working in imperial metrics, you can convert your miles that you work with into kilometers by multiplying your miles by 1.6. So what we'll start by doing is building a sample data frame of somebody who's running a 10-kilometer marathon, and then we're just going to tweak it a little bit to add some noise. So what we're going to do is set up an example individual. We're going to have them run a distance of 10 kilometers. Keep in mind that anything that has a hashtag before it or the pound sign before it is a comment, so R will not be calculating this or taking it into account during its calculations. So our duration is going to be about 30 minutes, and this individual's mass is 70 kilograms. Again, if you want to convert kilograms to pounds, you go kilograms times about 2.2. 70 kilograms times 2.2, and we have somebody who weighs about 154 pounds. So we want to know our speed. Our speed is then 10 kilometers divided by however many hours. So 30 minutes is half. So 30 minutes over 60 minutes per hour, and we get the individual speed of 20 kilometers per hour. So this is a pretty good pace that the individual is going at. It's a fast jog, nothing unbearable. So let's build the data frame. So we're gonna call it race data.frame, and we'll just start off with some simple stuff. Duration is 1 to 30. These are in minutes, and we'll have our speed is speed. So if we look at the top of this, the first 6 rows, we have this. So at minute 1, the individual is running at 20 kilometers an hour, 2, and so on. To add some noise to this, we're going to add just some random but normally distributed values, and then we're going to sort that to estimate or to assume that the individual is starting at a slower pace and increasing in pace as the race goes on. So we'll use sort, and then we're going to use absolute just in case there's negative values that would come up for whatever reason. We keep everything positive because this individual won't be running at negative speeds. So we have 30 values that we need. Our speed is the mean value, and 2 is going to be our standard deviation. So we'll close off all of this. If you'd like to get the same values as me, you could set your seed to, we'll use 1, 2, 3. Set seed. There we go. And then there we go. So forgot the R norm function. So that's randomly but normally distributed data. So we'll look at the head of race again, and we see that this person starts at 16 kilometers an hour and moves up. And if we wanted to see the last 6 rows, we can use tail. And here we have this individual moving up and finishing the race at 23.5 kilometers an hour. If we want to calculate the distance that they have traveled, we can use the $sign to explicitly state that we want to create a new column here. So we'll do race and then speed, and then multiply it by race times duration. But we're going to need this in kilometers per hour and not minutes. So race duration over 60, because there's 60 minutes per hour. And again, we'll look at what our race data frame looks like. And there we have it. So distance is how far they've traveled over time. And we see that it increases with speed. So what we need to do moving forward is estimate or calculate their VO2 max, or how much oxygen they're metabolizing per minute. And then from there, we can estimate, based on how many calories are burned per liter of oxygen, how many calories they've burned over the course of the race. So there's a few different formulas. We'll run through these fairly quickly. By using Control-Shift-R on a Windows computer, you can create a section, and you'll see that you can call it V.O2, and you hit enter, and you get this line, just so we have a little bit more clarity as to what's going on. So there's going to be a function that we're going to write, and this is going to be less than, for individuals moving less than 10 kilometers per hour, or 6 miles per hour. So we have walking VO2, and then our function is going to just need the individual speed. So let's go speed in metric. And this is going to be taken from Bunk and Dula, I believe. That's probably not how it's pronounced. And this paper was published in 1997. Their formula is VO2 equals, and this is going to be a little bit long to type in, but might as well figure out where the estimates are and what the differences are between a few of the estimates. So 4.501 minus 0.108 times speed in metric plus, and this is a quadratic, so we have 0.379 times, and this has to be squared, metric squared. And what we want is the VO2 value returned. And as always, you hit enter up here, or control enter, and we have this now saved in our environment right there as a function. So let's do that for another formula here, which we'll call jogging, or jog underscore VO2. And that's because it can take speeds that are a little bit higher. So function speed.metric. Just to make sure that we don't get confused, we could say jogging anywhere from 10 kilometers per hour to 17 or 18 kilometers per hour, based on what the authors suggest. So we'll open up the brackets here, the curly brackets, and we'll add in this formula that was published by Briswalter. So just so we know where it's coming from, and it was published in 1996. And the formula VO2, or V.O2, is 17.94 plus 0.00845 times our speed in metric. There we go. Plus 0.2093 times our speed in metric squared. Now we have two more that we're going to use, and then we're going to quickly see how they differ, and then apply it to our race data or sample data. So we have one that's treadmill running, and this is different from running on the track because the treadmill actually is more efficient because it pulls your leg back rather than you having to propel yourself forward. So it uses a little less energy. So we'll call it treadmill. treadmill running, and this is anywhere from about 8 kilometers per hour to 25 kilometers per hour. So treadmill underscore VO2. Again, all we need is the speed in metric. Open up the curly brackets, and this is published by Leger and Mercier in 1984. 1984. So we'll have our VO2 or V.O2, and that's equal to 2.209 plus 3.163. And this was all built off of just a simple regression based on breath by breath analyses that they did back then. So this is just taking their formula based on their sample size and the individuals that participated in their study. So it might not apply to athletes as well, but in general, this is a good understanding of a caloric expenditure and a good way to estimate a different type of player load. So we're just going to finish off here. So this 0.0005 to 5542 times our speed metric, and this is cubed, it's not squared. And we'll want to return our VO2. I don't believe you need to explicitly state that you want it returns, but it's always just good practice to make sure that you haven't missed any steps like I did here, where this would have returned nothing. It would have calculated things, the VO2 or V.O2 within the function, and then returned absolutely nothing. And then finally, we'll have our track running. And this was also published by Leger and Mercier. And it's applied to 8 kilometers per hour to 25 kilometers per hour. So we'll call it track underscore VO2. And we're going to write out this function. Again, this is slightly redundant, but it's good practice, and you really get the feel for how functions should be built. So we'll credit Leger and Mercier again. Mercier 1984. Let's add that right there. And this one's the the simplest one that we'll be building, and the one that we're going to be using moving forward. And all it is 3.5 times our speed metric. Now, we have to keep in mind that the V.O2 is so I'll put it here. V.O2 is in milliliters per kilogram per minute of oxygen that is used. And so we see 3.5, that's a rough estimate of our MET, which are our metabolic equivalent approximation of how many calories we burn per minute just while at rest. So here what we'll do is we'll just go from here all the way up to here and just hit Control Enter, and now we have our functions that are built in right there. So let's compare the VO2 or V.O2 estimates, V.O2 comparison, or compare, let's say, for brevity. So we'll have walk underscore VO2. You can hit tab when that comes up, just so you can, just for it to move a little bit faster. It's almost like shorthand. And let's say we'll take somebody who's moving at 10 kilometers per hour, just because 10 is a good overlapping value between all of our functions here. So walk, there we go. If we use the semicolon, everything on that same line will run. So jog underscore VO2, semicolon, treadmill, tread 10, and finally our track, and then 10. And if we hit enter, we see that we have slightly different estimates here. 35 is just 3.5 times 10, and that's what we're going to be using. We see that this value here, 41, is a large overestimate, and that's just because it is based on walking speeds, so below 10 kilometers per hour within a general population. So moving forward, let's now get into our caloric expenditure. So we'll Control-Shift-R for a new section, and then caloric expenditure. There we are. So we need to keep in mind that metabolizing 1 liter of oxygen takes about 5 kilocalories, or calories that are what we know of today that are seen on like food packages. That it's the same thing, or they're the same thing but under different names, and it's just a way to estimate, how much heat is needed within the body to break down the material or the whatever is ingested and to be used for energy. So our equivalent or estimate of O2 metabolism is 5 kilocalories or calories per liter of oxygen. And this is going to be important moving forward, just so we can estimate, based on our functions up here, how many calories this individual burns over the course of a 10-kilometer race. So we'll use CE for caloric expenditure, and we're going to write our function. And again, we just need our speed dot metric. So speed in metric. So VO2 underscore, VO2, or this is V dot O2 that we're calculating, is track underscore VO2. And then we're going to have this individual running at whatever speed they're going. And then we'll call it energy expenditure, just so we don't use CE again, just in case it overwrites for whatever reason, is going to be our VO2 value multiplied by 5 kilocalories per liter of oxygen times, and what we're going to get is our final units are going to be kilocalories per kilogram per kilometer run. So to do so, we need 60 minutes per hour. So we can get the 60 minutes per 1 hour. So we can remove that milliliters per kilogram per minute. So we need to get rid of that minute. Multiplied by 1 liter per 1,000 milliliters. And that's for our liters of oxygen that we're consuming. And then finally, we multiply it by 1 over our kilometers per hour, which is equivalent to hours per kilometer. So that way we can figure out or negate the speed, and then we can get just our kilometers. So that way we don't take duration into account. And to do so, we can then calculate our caloric expenditure for any given duration. So speed metric. And then we will return our energy expenditure. Go up here, Control Enter, and now we have that function. And we will now see that at any speed, our approximate caloric expenditure in kilocalories per kilogram per kilometer is always 1.05. So if we have 10 kilometers per hour or 20, it makes no difference. So let's add that onto our race data set. So let's just look at that again. So here we have it: duration, speed, and distance. So now what we're going to do is create a caloric expenditure column, and we're just going to use CE, the formula that we used, race, our race data set, and then multiply that by the speed. And we can look at our progress here. So now we have CE, which is 1.05, which is exactly what we figured out right there. And then we're going to want to know how many calories this individual burned, or kilocalories, over the course of the race. So we'll do caloric expenditure total. And here's where we need the calculation of race times caloric expenditure. Keep in mind that this is in kilocal per kilogram per kilometer. So to get our distance or kilometer, we have that here. So we have our distance variable, and we do know from above here that our individual weighs 70 kilograms. And then 70 kilograms. So let's not forget that. So that's going to come in handy right now. So we're going to multiply this by the distance they have traveled, multiplied by their mass of 70. So we'll hit Control Enter right there. And our last step here, we'll take a look, and there we have it. So we have an increasing amount of calories burned per minute. So to visualize this, Control Shift R, plotting, we're going to just quickly visualize this. So using a plot of speed over time, and then how many kilocalories they burnt over the distance or time as well. So we'll use race, the speed at which they traveled over the duration. And we'll get that. So we see that this individual started the race at about 16 kilometers per hour, then slowly increased their pace over the course of 30 minutes to about 24 kilometers per hour. And then finally, what we will do is plot our caloric expenditure total onto our duration. And there we have it. So you'll see this gradual, it's almost like a slight bow here. And that's because we have this gradual increase. And we'll see here that if we wanted to figure out the total or the final amount of calories that this individual burned over approximately half an hour, we can just hit tail and then call our race. And because they're moving at a fairly good pace, they've expended approximately 866 kilocalories during the course of this race. If you have any questions or comments, you can reach out to me at Aaron Z. Pearson on Twitter. You can also reach out to me by email. My best email is aaron@midsprint.io. This concludes our dive into player load or different player load metrics. And next week, we're going to compare and contrast the three metrics that we've used to see if there's any, if they're comparable, or which context, in which context we should use the given metric.